Okay, so let us continue with the solution of this problem. This is where we left in the class video. So the exercise here is this. G is the group of all 2 by 2 matrices of this form where the second row first column entry is 0 and the matrices are also non-singular, that is AD is non-zero. Under matrix multiplication, we have to show that the commutator subgroup or the derived subgroup of G, G prime, is precisely the set of all matrices of this form. So let us see what we can do in the solution. So in the beginning of the solution, so let's just start by naming this set of matrices something. Let N be the set of matrices of this form where X is any real number. Okay, and note that these matrices are already non-singular because each one of them has determinant equal to 1. By exercise 21 of section 2.6. We know that, so in that exercise we have already come across this set. N is a normal subgroup. Normal subgroup of what? Normal subgroup of G, and also the quotient G by N is abelian. This also was shown in that exercise 21 from section 2.6. So by exercise 5 part C, the commutator subgroup of G is contained in N. We want to prove that G prime is actually equal to N. So we have to show that the reverse inclusion is also true. N is also contained in G prime. So for that, now for any X belonging to R, any real number X, we have this element 1x01, this matrix, one can see that it is equal to this product 1 minus x01 2101 times the inverse of 1 minus x01 times the inverse of 2101. You can easily carry out the computation and you will see that you have this matrix. So that means any element in N is actually a commutator formed by two elements which clearly are from G. So this just shows that all the elements in N are also in G prime. So that gives us the reverse inclusion. This shows that N is also contained in G prime. So G prime is equal to N, and that's just what we wanted to show. So here the solution ends, and the last exercise of this set of exercises is exercise 21. Let S1 and S2 be two sets, two non-empty sets actually, because we are going to consider a function from S1 into S2. Suppose that there exists actually there is no need for S1 and S2 to be non-empty in order for there to be a function from S1 into S2, but that's not how functions have been defined in this book. Herstein does not allow anything called the empty function. That is there in Tau's analysis, but that we don't have any need for that function here. So for us, S1 and S2 are going to be non-empty, and there exists a one-to-one mapping psi of S1 into S2. Show that there is an isomorphism. There exists isomorphism of the group AS1 into AS2, where of course we again recall where A of S means the set of all one-to-one mappings of S onto itself. Okay. So we now need to define a mapping from AS1 into AS2. So the inputs of that mapping will be coming from AS1, that is the inputs will be bijections on the set S1, and the outputs should be bijections on the set S2. So we define the map like this. Define a map T from AS or okay, before we define this, we need to, okay, we cannot directly define it like this. Let F be a mapping in AS1. F is an element in AS1. That means F is a one-to-one mapping of S1 onto itself. Now we are going to define a map which we are denoting by the symbol Ft. Do not think of T as something else, okay, but this notation may be a little confusing. Huh? Let me use another notation. Tf which is going to be a map from S2 into itself by this formula. STF is defined to be equal to S itself if S does not belong to S1 psi. We will see what these things mean. And if S belongs to S1 psi and S is equal to T psi, where T belongs to S1, then we define the map to be this. Is it making sense? No, it will be the order will be the other one. TF psi. Okay, let us now see what we have written here. A small diagram will be helpful. This is our set S1. This is our set S2. Okay. Now we already know it is given that psi is a map that maps S1 into S2, and it's also given that psi, I mean we don't have that part, it's there in the exercise, that psi is a one-to-one map from S1 into S2. Now there will be an image of psi, I mean image of S1 under psi. That image is denoted by S1 psi. It has all the outputs and it's a subset of S2. We already know that. Now what we are doing is this. We are given a map F from S1 into itself. So F is a map like this. And using this map F, we are defining a map from S2 into itself. So S2 is that other map TF is a map like this. Now how is TF defined according to this definition? the inputs of TF should come from S2, the outputs also should be in S2. Now that input, since it's coming from S2, it can either lie outside this S1, okay, this S is looking like delta, no? S1 psi, it can either lie on the outside of S1 psi or it can lie inside S1 psi itself. So there are two cases, and if it lies outside S1 psi, then according to our definition of this map TF, the image of S is itself. Okay, but if S is lying inside, see, that's what we have written. If S does not lie in S1 psi, in the image of S1 under psi, then the output is defined to be S itself. But if S lies in the image of S1 under psi, then definitely S will look like this for some T belonging to S1, since it belongs to the image of S1, so it will, that particular S will be the psi image of some element in S1. Let that some element be T. Okay. Then what we are defining the output to be is this TF psi. Now this T is here somewhere. So when we apply F on T, what do we get? We again get an element in S1 itself, TF, some element in S1. Now on that, when we apply psi, we get some element in S2. So ultimately we are getting an element in S2. So as far as the map TF is concerned, I mean, it is actually taking inputs from S2 of course, but the outputs also lie in S2. Okay, so that much is clear. Now we have to show that the outputs are actually unique for a given input. For a given input, we can have only one output. That we must make sure in order to say that this TF is in fact a well-defined map on S2, or a well-defined map from S2 into itself. Okay, for that, let me just keep the figure like this. It does not form a part of the solution, but it's for our understanding. Okay. Now, if our input is S and if S is not in S1 psi, then S itself is the output. So in that case, there is no question of uniqueness of the output for the given input. But if S belongs to S1 psi, if this is the case, then the output ultimately is depending on T, and the output looks like this, the psi image of the F image of T. Now if T itself is not unique for our S, then there is a problem, because then we may possibly get different outputs for the single input S. Fortunately, that is not the case, and that comes from the fact that our map psi is given to be a one-to-one map. So the inverse image of S under psi, this T, is unique. Because of the one-to-oneness of psi, there can be only one inverse image T whenever it exists. I mean, this is the case where it exists, then the inverse image is unique. So we just simply write this. So what we are saying here is simply this: you choose S in S1 psi, for that S you get only one T, and that's why there is only one output in the second case also. So we write like this: since, or in fact let us just write the sentence like this. Note that TF is well defined because psi is 1 to 1. Okay. Now our next aim is to show that this TF, this map, is in fact itself 1 to 1. It's an injective map. So for that, let S1 and S2 be two elements in S2 such that S1 TF is equal to S2 TF. Now if we can show that S1 is equal to S2, then that would imply that TF is 1 to 1. Now cases will arise. If S1 and S2 are both not lying in S1 psi, we have to consider these cases because that's how TF has been defined. It has been defined partly. If none of them is in S1 psi, then by the definition of TF, S1 is equal to S1 TF, which according to our assumption is S2 TF, but that is equal to S2 because S2 also does not belong to S1 psi. So in this case we are getting the conclusion that the inputs are equal when the outputs are equal. Then if both S1 and S2 belong to S1 psi such that S1 is equal to T1 psi and S2 is equal to T2 psi. Psi where T1 and T2 belong to S1, then what do we get from this? Then we get this S1 TF. Then in that case, according to the definition of TF, is T1F psi. This is S1 TF, which according to our assumption is S2 TF, and that is equal to T2F psi. Now next we use the fact that the mapping psi is 1 to 1. Since psi is 1 to 1, we have from this equation T1F is equal to T2F. But keep in mind that we chose f to be a function not just from S1 to itself, but in fact f was chosen to be an element in AS1. So f is in fact a bijective function from S1 to itself, and hence f is 1 to 1 since f belongs to AS1, f is also 1 to 1 just like psi. Thus this last equation implies T1 equal to T2, which in turn implies S1, which is T1 psi, is equal to S2, which is T2 psi. So in this case also, if both S1 and S2 belong to the psi image of S1 such that their TF images are equal, then they must be equal. Here also, outputs being equal implies that the inputs are also equal. Next, suppose S1 does not belong to S1 psi, but S2 belongs to S1 psi, and let S2 be equal to, we can, if we want, we can again assume S2 to be T2 psi, but that is a different case. So let us just simply write T prime psi, where T prime is some element in S1. In fact, we already know, because psi is 1 to 1, this T prime is uniquely determined by S2. Then S1 is what? Because S1 does not belong to S1 psi, by the definition of TF, S1 is equal to the S1 TF image of S1. Which according to our assumption is also the TF image of S2. But this now will be equal to T prime F psi. Okay, and this okay, now note one thing, since T prime F belongs to S1. Why? Because T prime is in S1 and F will map any element of S1 to again an element in S1. So this is in S1. So its psi image will be in the psi image of S1. Which is a contradiction. What is being contradicted? Namely the fact that, oh, I wrote S2 here, it is S1, because ultimately we are getting S1 equal to this. The thing that is being contradicted here is that S1 does not belong to S1 psi according to our choice, but this shows that S1, this says that S1 belongs to S1 psi. So this is a contradiction. So that's why if we have this assumption S1 TF equal to S2 TF, then this case cannot occur, that S1 does not belong to S1 psi but S2 belongs to S1 psi. Similarly, we cannot have S1 belonging to S1 psi and S2 not belonging to S1 psi. If we want their TF images to be equal, that also, this other case also cannot occur. In the, I should not say remaining, so we can just conclude like this. Thus, if S1 and S2 belong to S2 such that S1 TF is equal to S2 TF, then in the other cases we have already shown that S1 is equal to S2. This shows that TF is 1-to-1. TF is an injective mapping. Next, we want to show that TF is onto. So for that, let us choose any element here. Next, let sigma be any element in S2. If sigma does not belong to S1 psi, then sigma is the TF image of sigma itself. Okay, so sigma appears as an output under the function TF. If on the other hand sigma belongs to S1 psi and sigma is equal to, say, S we can take anything, sigma equal to mu psi, where mu belongs to S1, then we want sigma to appear as the TF image of something. Is it really the way to oh yes, okay, then sigma can be written like this. Sigma is mu psi. Now mu can be written like this: F inverse F, the space is not enough here, this is equal to mu F inverse F sine. Does it make sense? Mu is an element in S1. Okay. Now F is a function from S1 to itself, which is of course bijective. That's why we are able to write F inverse. So F inverse mu is again an element in S1. On that we are applying F, and clearly because F is bijective, F inverse, if we calculate this, we are going to get mu. F inverse and F, they have the opposite effect of each other on an element. Okay, so now what do we have? Can we write this as mu F inverse TF? Is it going to be mu F inverse TF, or no, not mu F inverse TF, mu F inverse psi TF of that, and in brackets we write, note that mu F inverse psi belongs to S1 psi. Do you get what we have done here? This step is okay. Now in this step, from here to here, we note just simply this. We have some mu F inverse in S1, and that has been mapped onto mu by F1. Okay. Now since mu F inverse is in S1, so its psi image is in the psi image of S1 here somewhere. So because it's in S1 psi, so according to the definition of TF, if we apply TF on this element, then on this element, this inner element, we will apply F, and on that result we will apply psi. So we are in fact getting this. So because this element is in S1 psi, so automatically this element is also in S2, and that is the input for which the output is sigma under the map TF. Thus, or this shows that TF is onto. We have thus shown that TF is both one-to-one and onto. So it's a bijective map from S2 to itself. We thus have TF belonging to AS2. Now define a function which we have denoted here by what I don't, okay, we have denoted this one by T from AS1 into AS. Now we are in a position to define that function by this ft, the T image of f where f is an input which is coming from AS1 is defined to be equal to TF. We have shown in the above paragraph that if we choose an f from AS1, then this particular function TF for that f is actually a bijective function or is actually in AS2. The previous paragraph shows that T is well defined. Okay. Now our aim is to show, next aim is to show that T is a homomorphism, because these are groups we already know. Now let F and G be two maps in AS1, two elements in AS1. So for these elements, to prove that T is a homomorphism, we have to show this. F composition G, on that if we apply T, then we get Ft composition Gt. Note that this means what? F composition G is an element in AS1 because we are composing two elements in AS1. That will again give us an element in AS1. This is the binary operation in AS1, composition of mappings. So on that, if we apply T, we are getting an element in AS2, which is a function from S2 into itself. On the right hand side, we already have two elements in AS2, Ft and Gt, and they have been composed. So that again is an element in AS2. So this is the right hand side also is a mapping from S2 into itself. We need to show that these two maps are equal. This equality we need to show. So that means these two maps should map any element of S2 onto the same element in S2. So we need to show that if we choose any element S in S2, then this image is equal to this image. That's what we need to show. So let us now proceed with this. Let S be any element in S2. Okay. So the way we have defined TF, two cases will arise, and we have to look at the two cases separately. Two cases will arise, or in fact many cases will arise. Let me just think of it. So F and G, then for any S1 we have sides. Okay. Let us start, and if something we need something more than this current understanding of the situation, then we will handle that then and there. If S does not belong to S1 psi, then I think now we can wrap this part up. Then what is this? F composition G T. First of all, by the definition of the function t, this itself is Tf composition G. Okay. Now S does not belong to S1 psi. So this is equal to S itself, and that is also equal to S Tf, or if this I am getting confused myself. This is equal to S, and let us also calculate the other side separately. Have I taken S1 here? No, it's not S1, it's just simply S, and S Ft composition Gt, which is just S Tf composition Tg, which is S Tf Tg. Because S does not belong to S1 psi, so STF is S, and again because S does not belong to S1 psi, so STG is again equal to S. That is on the other hand, if S belongs to S1 psi, and because of that S is equal to T psi, where T is some element in S1, then here also I think it will be safe to do the two parts separately. You may be seeing all these things in your mind pretty easily, but I am a very slow thinker. Tf composition G, so that is equal to, okay, now first of all on this T we will apply F composition G, and on that we will apply psi. That's how we define Tf composition G. So this means Tf G and psi. It's just this, and if we calculate the other side, Ft composition G T, this is equal to, first let's handle what happens inside. Tf composition Tg, so this is equal to by the simple definition of composition STF and TG image of that. Now again, because of this case, this situation, STF is TF psi. Okay, now what about TG? We are no longer applying TG on S. We are applying TG on this element. Now this element, from the look of it already belongs to S1 psi. Why? T is an element in S1. So F is a mapping in AS1. So TF is again an element in S1 because F maps S1 into itself. So TF is an element in S1, so automatically this will be an element in S1 psi. So on that we are applying TG. So we will have to use the second part of the definition of TG. And that's why this is equal to TF G psi. Okay, and these two things are matching, that is in this case also S F composition G T is equal to S FT composition G T. Thus, as functions, these two things are equal. Both the left hand side and the right hand side are the same function from S2 into itself. This shows that our function T is a homomorphism. Now we need to show that T is an isomorphism. I mean, we are looking for an isomorphism from AS1 to AS2, and this is our candidate. So next, let F1 and F2 be two elements in AS1 such that their T images are equal. We need to prove that the functions F1 and F2 themselves are equal. That would prove that T is 1 to 1 and hence an isomorphism. Then, by the definition of T, capital T, Tf1 is equal to Tf2. Okay. Now we need to show that F1 is equal to F2. So, for any S belonging to S2, we have STF1 equal to STF2, because don't forget that these functions TF1 and TF2 are after all functions from S2 to itself, S2 into itself. So it will have they will have the same effect on any element of S2. But the question is, do we really need to write this line? Because after all, we want to show that f1 is equal to f2 and f1 and f2 are functions from S1 into itself. Okay, so there is no extra advantage in writing this line. Instead, let us take an element in S1. So for any S belonging to S1, we have S F1 psi is equal to S psi TF1. Since S belongs to S1, so S psi belongs to S1 psi, capital S1 psi. So by the definition of TF1, the TF1 image of S psi will be equal to this. But then because of this equality, we get S psi that is equal to S psi TF2. And this again is, by the definition of TF2, SF2 psi. So we get the fact that SF1 psi is equal to SF2 psi. But now use again the one-to-one-ness of psi. Since psi is 1 to 1, so this last equation implies that SF1 must be equal to SF2. But S was any element in capital S1 and the F1 and F2 images of S are same. So the functions F1 and F2 themselves are the same function. Thus, F1 is equal to F2. So that's it. We assumed F1t equal to F2t. We have proved that F1 is equal to F2. This shows that T is 1 to 1. P is thus an isomorphism of AS1 into AS2. That's what we wanted, and now everything is done. This solution turned out to be more confusing to myself, to me, than what I previously thought. T is thus an isomorphism of AS1 into AS2. So this completes this set of exercises, and now we start the next section on automorphisms. Because of this much time that we have used in the previous exercise, we won't be able to see as much of automorphism in this video itself as I hoped initially, but we will go far enough. So let us start the section with some initial words. In the preceding section, the concept of an isomorphism, we have just now seen one isomorphism. Of a group into another group was defined and examined, like this exercise. Now, a special case of this situation occurs when the two groups are the same. That is, if we consider an isomorphism of a group into itself. The special case in which the isomorphism maps a group into itself should be of interest, because due to its special nature, it may give us some more information than what we normally get when we consider an arbitrary isomorphism between two groups. Should be of some importance. We use the word into advisedly because let me first refill. I don't think it has enough ink. groups do exist where you can find, I should not say you can find, but there are isomorphisms from a group into itself which is not necessarily onto. I mean, such isomorphisms exist. Which have isomorphisms, or let's just write the sentence like this: groups G to exist which have isomorphisms that are into but not onto G. Such isomorphisms are there. So if we are additionally saying that an isomorphism is onto, it is extra. Okay, it's not always the case. And one example is this. Let G be the group of all integers under addition. Define the map T from G into itself by this formula, where an integer x is mapped onto its double, which is again also an integer, and this map is clearly a well-defined map. For two integers x and y, we have this. If you apply t on x plus y, that by the definition of t is its double, which using elementary properties of integers equals 2x plus 2y, and that is equal to xt plus yt. Thus, T is a homomorphism also it's easy to show that T is 1-to-1. In the text it's shown, but of course it's almost obvious now. If the T images of two integers are equal, that is, if the double of two integers, if you take twice of two integers and they are equal, then the integers themselves are equal. So that's why T is 1-to-1. So T is an isomorphism. Of the group of integers into itself, but T is not onto because the images under T are all even integers, so odd integers are left out. Because for example 1 is, or in fact let's just also mention that 1 is an element in G, is not equal to the T image of any element in G. So that's why isomorphisms exist which are not necessarily onto. Now, but what happens when they are onto? Of greatest interest to us is the case when an isomorphism maps a group, or let's just write an isomorphism of a group is onto the group. And this prompts the next definition. An automorphism, or by an automorphism, of a group G, we mean an isomorphism of G onto itself. So that means there are a number of things happening with an automorphism. You have a group and there is a one-to-one onto function from the group into itself, that is a homomorphism. Such a function is known as an automorphism. The power is gone. Anyway, it has come back also. As mentioned in chapter 1, never forget that an automorphism is not merely a bijective homomorphism, but the domain group and the, if I call it codomain, the second set in the function, they must be equal. Okay, if they are not equal, then that is simply a bijective homomorphism or an isomorphism of one group into another group, onto another group. For automorphism, the groups must be the same. So, as mentioned in chapter 1, it is that typical Herstein thing, deciding or trying to decide on which side we should write a function. Whenever we talk about mappings of a set into itself, we write mappings on the right side. I have tried to follow this rule itself irrespective of what type of mapping we are dealing with throughout this book. Okay, I try to write mapping on the right side because that's what we are using, and it really matters in some cases on which side you write the mapping, whether you are writing xt or t of x. That matters sometimes, and especially, as you already know, it matters when we are dealing with composition of mappings. So to maintain uniformity, I have tried to always write mappings on the right side, but if I inadvertently wrote mappings on the left side anywhere, then you see what I have written is actually sound or not. If it is not logical or if I made some mistake, please let me know. Mappings on the right side. So if T maps a set S into itself and X is an element in S, then xt is the image of X under T. Herstein is mentioning this again because in this section itself he uses this notation as well as the other notation simultaneously and very confusingly, and I don't know why. What is the reason for using the other notation? This itself, since we are using such a thing, so let's just stick to it. Okay, so now we have the definition of an automorphism of a group. Let us now investigate the automorphisms of any group. Let G be any group consider the identity map I on G, which we already know is given by this definition. Every element is mapped onto itself. We already know that I is bijective. This we have seen even before we started group theory. In the section on functions, there itself we saw that the identity map is both one-to-one and onto, and it's almost obvious to see why that is the case. I is bijective. Also, I is a homomorphism. This is also something we know from our very first examples of groups that we discussed after giving the definition of a group. In fact, the very first example, it had two mappings. One of them was the identity map, and the other is the constant map mapping every element of a group onto its identity. So these were two trivial cases of homomorphisms. So that means this is an automorphism of G. So automorphisms of a group really do exist, and in fact any group has at least one automorphism, which is this identity automorphism. Okay, let A of G, this type of A, denote the set of all automorphisms of G. We thus have I as an element of this set. So that means this is a non-empty set. This implies this is a non-empty subset of A of G. Okay, what is this last line? Recall that for a non-empty set S, A of S denotes the set of all one-to-one onto mappings of S to itself. In other words, A of S has as elements in it all the bijective mappings with domain S and codomain S. And we have already seen that A of S is a group under composition of mappings as the binary operation. Now we are saying that this is a non-empty subset of A of G. This is non-empty, fine, because I is here. But how is it a subset of A of G? That is because you see, the set that we have here for in this particular case is G, is the group itself. So A of G is as a set, it's the set of all one-to-one onto mappings of G to itself. G itself is a group, but we are not considering that fact for a moment. G after all is a non-empty set. Being a group, it's a non-empty set. So for that we can form this A of G, and we know that A of G itself is a group under composition of mappings. Now this is also a group, that other A of G. What are the elements in this? The elements are automorphisms. So if I choose an element F here, then F is an automorphism of G. That means F is a homomorphism and F is also a bijection, one-to-one and onto. So that means in particular F is a bijection from G to itself, and that just implies that f is in A of G. So this always is a subset of A of G, because in this we are considering those bijections that are homomorphism of G. So now because of this, it becomes a non-empty subset of A of G, and we already know that this is a group. Can we now show that this is a subgroup of A of G? Subgroup means the binary operation will be the same. Is that true? If that is true, then not only shall we have a subgroup of A of G, but that in fact will in particular prove that the set of all automorphisms itself is a group in its own right under composition of mappings. We are now going to show that yes, that is the case. We now show that I am unable to write this A. I mean, I really cannot write it beautifully. We now show that this is a subgroup of A of G. For that usual thing, we consider two elements here, show that they are when you take their product in the group, in this group, that product belongs to this, and the inverse of any element in here is again in that set. So let T1 and T2 be two elements in this. This means T1 and T2 are automorphisms of G. First we have to show that T1 composition T2, because the binary operation is composition, keep that in mind. T1 composition T2 is again a homomorphism and also bijective, but the bijective part we already have. We know that when we take the composition of two bijections, then that is again a bijection. We already know that T1 composition T2 and T1, not just that the composition is a bijection, but the inverse of a bijection is also a bijection. These are results we know from our second section of the first chapter, where we treated functions. These are bijections on G, that is, or in fact there is no need to write that is. So now let G and H be two elements in G. We have GH T1 composition T2 equal to, by the definition of composition, this is GH T1 and the T2 image of that. Now since G and H are in G and T1 is a homomorphism of G, so this inner element is equal to GT1 HT1. Again, because of the fact that T2 is also a homomorphism of G and GT1 and HT1 are again in G. Why are they again in G? That is because T1 maps G into itself. So these elements GT1 and HT1, these T1 images, are again in G. So now because of the fact that T2 is a homomorphism, GT1 T2 times HT1 T2. Then again you use the definition of composition of mappings, you get this. Thus, T1 composition T2 is a homomorphism, and being a bijection, it is thus an automorphism of G. Which, however, we will conclude after we do the other calculation. Also, note this: GH T1 inverse T1 is equal to GH, because T1 inverse T1 is the identity mapping, which when you apply on GH, you get GH, and just like that, G is equal to GT1 inverse T1, and H is equal to HT1 inverse T1. Now in the next step, we use the fact that T1 is a homomorphism. So this becomes equal to GT1 inverse HT1 inverse T1. Keep in mind that these are elements in G, because we have only one group in this situation. Since T1 being an automorphism, T1 is bijective, so T1 is on 1 to 1. Since T1 is 1 to 1, so from the above equation we have this GH T1 inverse equal to GT1 inverse HT1 inverse. So T1 inverse is a homomorphism to being bijective T1 composition T2 and T1 inverse are thus automorphisms of G, that is, they both belong to the set of all automorphisms of G. This is a subgroup of A of G and thus is a group in its own right. And that is the first lemma of this section. Lemma 281. So whatever we have proved, we are stating it as a result. If G is a group, then A of G, the set of all automorphisms of G, is also a group. The text does not mention the binary operation, but from the situation you can see that the binary operation is the composition of mappings, because here the binary operation is composition of mappings. Okay. So we have just managed to show that the set of all automorphisms of a group itself is a group under composition of mappings, and we have so far shown that in that group we always have the identity automorphism, but that is clearly not something very interesting. We now want to know whether other automorphisms also exist. So that is the next inquiry, and that, okay, let us just continue a little more. Of course, as yet we have no way of knowing that this in general has any element other than I, the identity automorphism. And the thing is that if the original group G has at least two elements, then the automorphism group, we call this group the automorphism group of the original group G. Then the automorphism group also has other elements which are non-trivial automorphisms, that is, which are different from I. For groups G with more than one element, that is, for non-trivial groups, this has elements, or in fact let's just call it that also. I mean, let's introduce that term. It has non-trivial I should not say this has non-trivial automorphism, because this may give the wrong message that we are talking about an automorphism of this group itself. Non-trivial element, that is, elements other than I. And this is a statement we are going to prove in the exercises. This is one exercise at the end of this section. Let us now look at the two types of groups separately, that is, abelian groups and non-abelian groups. And in each one of them we ask this question: if G is an abelian group, that has at least one element x naught satisfying this, x naught is not equal to its own inverse, then we can construct a non-trivial automorphism of G as follows. Define the map T from G to G by this formula. The image of any element x in G under T is x inverse. Okay, this is a well-defined map because every element in a group has an inverse and that is unique, and which again is an element in the group. Now next we want to show that this map is a homomorphism. Let x and y belong to G, then x, y, t is, by the definition of T, this is the inverse of x, y, which we already know from elementary properties of a group, is equal to y inverse x inverse. But since we are in an abelian group, so this can be written as x inverse y inverse. So this is xt y t. Thus T is a homomorphism. If G and H are in G such that their T images are equal, then the T images are nothing but inverses, they are equal, and hence the elements themselves are equal, because G is equal to the inverse of the inverse of G. This also we know from that elementary lemma that we got in the beginning in group theory, but that is equal to the inverse of the inverse of H, because these two elements are equal, so their inverses are also equal, and this again is equal to H. So then G and H have to be equal. So T is 1 to 1. Next, or in fact we can write here itself also, since G is equal to G inverse inverse, which is the T image of G inverse. So every element in G appears as the T image of something, namely its own inverse. T is onto. So T is a homomorphism, that is mapping G into itself, that is both 1 to 1 and onto. So T is an automorphism of G. This shows that T is an automorphism of G. Okay. Now, what happens when we apply T to that particular element x naught, which is not equal to its own inverse? Then by the definition of T, this is x naught inverse, which because of our choice of x naught is not equal to x naught. So that means there is some element x naught in G which T does not map onto itself. So this implies T is not equal to the identity automorphism, it is something else. So that's how in any abelian group where there is at least one element which is not equal to its own inverse, we can find a non-trivial automorphism which is different from the identity automorphism. And we are next going to see the case where the group is non-abelian. And in case of non-abelian groups, surprisingly the task of generally see, abelian groups are somewhat always easier to study and easier to deal with because of commutativity. Non-abelian groups usually are much harder than abelian groups. However, in this particular case, surprisingly, the task of finding non-trivial automorphisms is much easier than what we have in abelian groups. So, in the next paragraph, the author writes this. However, the class of abelian groups is a little limited and we should like to see some non-trivial automorphisms of non-abelian groups. Strangely enough, the task of finding and in this context, non-trivial automorphism means an automorphism that is different from the identity automorphism. Is easier than the abelian ones. In fact, next we are going to see some particular types of automorphisms, and a byproduct of that discussion will give us the fact that in non-abelian groups we do have non-trivial automorphisms. The type is called inner automorphisms. We are now going to see some particular some particular forms of automorphism which will be called inner automorphisms. That, however, we will do in the next video. So I am ending this video, this part here itself, and if you want to say something, you can write in the comment section, or you can mail me here. Tomorrow I think there is calculus video in the schedule, but besides that, as we have already discussed in the previous video, previous video means yesterday's video, we will also see a Gaussian video. In fact, a Gaussian video is the prime focus. Along with that, there will be calculus if time permits. So that will be all for today. So this is me. Until the next video, this is me, Lucifer, from a mathematical room. Have a nice night.